Well, good afternoon. I know it's been a really long day, a long and packed day, and I'm between you, dinner and drinks. But I'm really excited to be here with you and share this topic because this conference is all about the impact of becoming digital. So what happens when humans become digital? And so the place that we're going to start is here. Does anybody recognize this gentleman? Show of hands. He was actually a speaker at DLD several years before. His name is Hugh Hare, and I want you to take a look at his legs. He's a double amputee, and you can see that he's wearing bionic legs. He lost his legs in a climbing accident when he was about 18 years old. And what he did was he took the normal prosthetics and he modified them so he would become a better climber. And in fact, to this day, he not only still climbs, but he's built an entire bionics company to customize limbs for amputees. So augmentation, he really believes in a new movement of neuro-embodied design. And I'm here to tell you that it doesn't just stop with double amputees. So let's continue the story. This is Neil Harbison. And when Neil was 22 years old, he decided that he was going to deal with his color blindness. Now, he has a form of color blindness that made him see the world in grayscale. Now, that device that seems to be sticking out of his head, it looks very much like one of those lamps that you use beside your bedside to read books. In fact, it's a multispectral camera. And it took him 5 surgeons to find someone who was willing to embed it in his skull. And what happens is he images the world with this camera in the visual electromagnetic spectrum in a wider swath than our human eyes can see. And that information is translated into vibration, which he hears. Now, that device also has an internet connection. And so he can receive signals from friends of his all over the world. And he allows 5 of his friends to signal him via satellite, sometimes even when he's sleeping at night. And some of those vibrations, he says, enter his dreams. So we'll continue, and this is Moon Rebus. She's a childhood friend of Neil Harbison's. She has absolutely no deficits, but she does have implanted seismic sensors. She, in fact, is an artist. She is a seismic dancer. She dances to earthquakes. And she and Neil founded something in 2010 called the Cyborg Foundation. They also both, incidentally, have a tooth that can communicate via Bluetooth, and since they both know Morse code, they often communicate by clicks on their teeth. So this is a real movement. This is something that is really happening. By the way, Neil Harbison also put a solar clock in his head. And so what happens is when it's midday, GMT, he actually feels heat at the center of his head. And by the time the heat moves around to his right ear, it's midday in Louisiana. All right, so what I show you now is a survey of the kinds of augmentation taking place. This is John Halamka, who is a colleague of mine. He's actually an individual. He's a physician. He has the first RFID implant. Here you can actually see the surgery. It's actually just an injection where the RFID device is being implanted. And why did he do this? It's got his medical records. So if he's ever found down, he has an implant of his medical information available. Now, others are doing different things with that. So Kevin Warwick has an RFID implant as well. But he's much more interested in doing things like turning his HVAC on and off and controlling his lights. And if you were interested in what else you can do, you can turn your body, an entire surface. So SkinPut is a way of taking these sorts of vertical waves that are input as you use the surfaces on your hand and forearm. They're interpreted by a monitor that this gentleman is wearing around his bicep, and they're converted into signals. However, you're going to see electronics are being miniaturized at this moment. It's getting to the point where you could get a sensor like this simply by putting a tiny slit in your skin and inserting something underneath. So how many of you would augment yourselves? Show of hands. There's at least a few people in the audience. This is a movement, right? I would replace my arm with a robotic one. Well, why wouldn't you? You might be smarter and stronger if you could replace your organic body parts with others that are available. Now, this cyborg movement has really helped people with disabilities. So in Zurich, they have something called the Cybathlon, and this allows people who have disabilities to compete using bionics and brain-machine interfaces. But these devices, these robotic devices, are getting even more sophisticated. This is the Luke arm, which was actually produced in collaboration with funding from DARPA, which is the Defense Advanced Research Projects Agency in the United States. And this is getting into an era where robotic arms for amputees and legs can be controlled by both brain signals and by muscle signals. Now, this is a very expensive device. It costs about 50,000 US dollars, so about 50,000 euro. However, this device was one of the clear winners at the last Consumer Electronics Show in 2020, just a few weeks ago. And it's because BrainCo, which has produced this arm, has now brought the price down to about 10,000 US dollars. So you can imagine how useful this will be to future amputees. And other advances in robotics, such as things coming out of Zen Bao's lab, will make these even better. So for instance, she's developing stretchable electronic skin that gives sensitivity to robots that is so exquisite that they can actually feel what they're touching. They get haptics, and in this particular picture, you can see that this robotic skin is sensitive enough that the robot will not squash this blueberry. But this is not just about a robotics evolution. Augmentation doesn't just stop there. This is truly about a brain-machine interface revolution. So anybody, you can call this out. Does anybody know what is the oldest brain-machine interface? Anyone? It happens to be a cochlear implant. These are placed often in children who have hearing loss at birth that is detected. And what these implants do is they transfer sound waves coming from the outside. They turn them into electrical signals, which are played sort of spatially on their inner ear and sent to their brain. And most of these children develop with normal speech and semi-normal hearing for their entire lives. And we've moved into other sensory domains. So new things like bionic eyes are being developed, which have sensitive photovoltaic arrays that sit at the back of the retina. It's almost like having a tiny little solar array there. And some of these devices are being miniaturized and made totally bionic. But the most amazing advances have been in the realm of movement. So this consortium, BrainGate, the title says it all, bridging the gap between brain and limb. And here you see Lee Hochberg. Lee is the principal investigator of this entire academic consortium. And what the consortium aims to do is to give movement back to people who are paralyzed. And these are people who are paralyzed from the neck down. Now, these people are cognitively intact. So the question is, can you receive information coming from their brain and send it to an actuator outside them because their spinal cord is not working? So what you're going to see in this video is an array, 96 little metal spikes. They're about the size of a baby aspirin, and they sit in the motor cortex. Here you can see real neural signals that are being recorded. They're being interpreted by a machine learning algorithm. And this woman who is paralyzed from the neck down is able to direct a robotic arm to bring a carafe of coffee to her mouth using her mind alone. So I'll say this once again. This is an example of a mind-controlled robot. Now, in Switzerland, they've been trying to build on this by reconnecting this sort of output from the decoder and the array back to a spinal cord stimulator. So people who are paralyzed might be able to reuse a spinal cord that has been injured. So there's a lot of entrepreneurs who are really excited about this idea of mind reading and brain-machine interfaces. So the most famous of them is this guy, Elon Musk. So I'm going to assume everybody recognizes him, right? Okay, so he doesn't just build rocket ships. He doesn't just build electric cars. In March of 2017, he made an interesting announcement. Suddenly, he was getting into the brain-machine interface game, and people were attributing this to his fear of AI taking over. If you talk to him about it, it's really not that. He just really saw this as the next interface. But I hadn't heard anything for a very long time. I have a couple of friends who were like in the first group of 10 employees. They were in stealth mode. And then suddenly, last summer, this announcement came out. So this is an excerpt of the abstract from bioRxiv. And what you see is this. That brain-machine interface that I showed you before had 96 electrodes. They're sharp, they're somewhat thick, and they can damage the brain. They also don't have as much fidelity as you'd like, because if you can decrease the size of your electrodes and pack more electrodes in, you can digitize a lot more information coming from the brain. So what were the advantages of this system? Well, they announced that they had been able to increase and pack into a single array up to 3,100 electrodes. Okay, so that's a couple orders of magnitude better than what we were doing before. And the way they achieved this was by putting them on these thin electrode threads, which also didn't damage the tissue. The chip that was used requires a lot less power consumption. So the brain essentially can get burned if you put a chip that is too high power next to it, which is why a lot of these devices, I don't know if you remember from the image of the woman who was moving the robotic arm with her mind, she had this big thing sticking out of her head with this massive cable. At this point, they have developed an array that will connect to the outside world with a USB-C port. So that's all you will have sticking out of your skull. Here's the thing. It is really hard as a surgeon to get electrode threads into the brain. It's almost as if you were sewing Jell-O. So they developed a neurosurgical robot that looks very much like a sewing machine. Here is a comparison in the size. This is the kind of electrode that we use for Parkinson's patients who get a deep brain stimulating electrode. You can see how small and how much less damaging one of these neural threads is. And this is a video that shows you how this new neurosurgical robot, which really looks like a sewing machine, can punch through these electrode threads into agar, which is a good simulacrum of the brain and what that tissue feels like. So kind of amazing advances taking place in brain-machine interfaces. But all of this would not be possible if it weren't for our ability to map. And our mapping has been getting better and better. Now, we've had lots of technologies. Some of them are older technologies. We've had the electroencephalogram, fMRI. We've had electrode arrays that are flat that we put directly onto the brain's surface. We've had PET imaging. This is an image of something called the human connectome. This is the highway between all these nerve cells. This is how they actually communicate. Now, we can do some crazy things by doing this kind of brain mapping. This is an image of me mapping a brain in the operating room. So why would I do that? Because I can actually watch my patients' brains transition between different levels of consciousness and try and understand the underlying neural networks. And myself and other physicians who basically study patients who are either sleeping, anesthetized, or comatose, we can look to see what brains that are more depressed have in common and begin to understand what the process of human consciousness is all about. But the place where this gets really spooky is when we start applying brain mapping to the visual system. So I'm going to set up an experiment for you. This is Jack Gallant, and he works at UC Berkeley. And what they did was they took a number of students and they put them into an fMRI machine. That's essentially a scanner, and it's non-invasive. And what they did was they presented a number of YouTube video clips to them. They had the students watch, and they gathered the activity coming from the back of their brains, the visual cortex. And then they looked at the images themselves. They looked at statistical properties of the images, lines, edges, colors, movement. And they created a data dictionary between the brain activity and what they saw on the video clips. So that's, if you guys are familiar with how machine learning is done, they were the training set. Then they took a whole new set of students, new set of video clips, and presented them. And this time they used the algorithms they had developed to see if they could figure out what they were seeing while they were blinded. And what you see on the left-hand side is the presented video clip. And what you see on the right is the reconstruction using the algorithm. And this, I hope you realize that this is quite amazing. Without cracking open anyone's skull, you can piece together what it was that they were seeing, right? So it's a form of mind reading. And the Japanese built upon this by building something that could read people's dreams. They combined fMRI and EEG. They waited till their subjects fell asleep. They waited till they were dreaming, pulled them out of the scanner, and had them report dream dictionaries, or dream journals. And then they would correlate what they said in the dream journal to the activity they were recording to reconstruct the subject of their dreams. So how many people think that's kind of a cool idea? You can get into a scanner and have your dreams read. Okay, there's a lot more hands because I am not cutting open your heads. But I would warn you about this. As Bob Dylan said, if my thought dreams could be seen, they'd probably put my head in a guillotine. And it's something I want you all to hold because people are using brain mapping for all kinds of things now. This is BitBrain. It comes out of Zaragoza, Spain. And they're using very simple consumer devices to assess people's engagement with products. So this is a form of neuromarketing. This is Poppy Crum. She's the chief scientist for Dolby Labs. And essentially, she's able to use an infrared camera to do thermal imaging on people's faces and assess emotion, affect, and levels of engagement. Now again, if you guys all have IoT devices at home, you might wonder with every software update or when you get the latest hardware, I mean, who reads your EULA before you sign it, that 20-page document that comes with your device? Okay, that is a 0 for the room. I have started reading them, but they take forever. So this is a problem. But there's another problem, and this one is even weirder, okay? So let's say I could read your thoughts, and I could read a memory. How many of you think, how far do you think we are from implanting that memory into another brain? So shout out numbers. How far are we from that? Okay, think about the future. Okay, I heard a 20. I heard a 20. Sorry, did I hear a 5? 2. Okay, it's like The Price is Right, if you guys have ever seen that game show. Anything else? Anybody else have an idea? 6 years ago. 6 years ago. So I'm going to set up the experiment because it's a creepy experiment. So here we go. This stage is a cage, okay? I'm a rodent, and I'm moving through this cage, this space, and over here there's a tiny bit of electricity. It's not enough to hurt me, it's enough to be unpleasant. So if I walk over here, my little paw touches it, and I get a little shock, and I say, okay, I'm not going back there anymore. If you record this activity from that brain, you'll get 2 things. One is something called a fear avoidance response, but you also get a spatial map of the cage. These are both 2 kinds of memory. Now you take a new animal, new cage. Cage is not electrified. You can inject the code you just discovered and recorded from one animal and put it into the brain of the other, and they will have a fear avoidance response and behave as if that part of the cage were electrified. So what I've just told you is we already know how to move some memories from one organic brain to another. That is what learning the neural code has done. And then just in the middle of last year, this was taken a step further. The idea was if you could, from recording in other places, figure out what the neural code was for something, and in this case, it was an odor memory, could you recreate that by stimulating the brain in the right way? And in fact, it turns out you can. So if you know what the code is, you can now recreate a memory of something that people have never experienced. You can move that into another brain. Now, if that's not weird enough, look what else you can do. So in this particular study, the researchers put some surface electrodes on the heads of people who are typing in passwords, and they were able to read their passwords. Okay, we are getting to a point where you're getting smartphones that are telling you to give up a fingerprint, a retinal scan. What happens when, for security, you're asked to give up your brain waves. And it turns out these researchers, by the way, weren't able to do anything about it unless they injected sufficient noise into the signal so that the signal could not be properly read. So what about identity? Can you tell identity from a brain map? Well, Sarah Laszlo could. So what she did was, in her lab, they put on these electrode arrays of about 30 surface electrodes again, and they showed their subjects images. And simply for a few seconds, by recording the electrical activity in their brain, they could identify them with 100% accuracy as an individual brain print. And they slowly decreased the number of electrodes till they got to 3, what you'd find in a typical consumer device. So that could be very secure, or it could be a means of invading your privacy. And in fact, as you'll see here in this Stanford study, what the researchers did was they took an older database of EEG from alcoholics, and they ran an algorithm, they trained an algorithm on that, and then they used that same algorithm on a new set of subjects, new set of data, and were able to correctly identify 25% of the alcoholics in the sample, even those who did not drink. All right, now they said they were doing this to help people who had addictive personalities, to help them to target people who might be at higher risk. But what if your insurance company started requiring this? Or what if you went for a job interview and instead of peeing into a cup, they wanted to sample your brainwaves, right? What if you have schizophrenia in your family? What if you have some other mental disorder? How might you be discriminated against? And that's why this idea of data and privacy becomes so important. And it's not just important because of what they can read and steal, it's important because of this. So several years ago, a group of white hackers at something called the Black Hat Conference attempted to hack a pacemaker made by a company called Medtronic. They make most of the world's pacemakers. And they were extremely successful in either eliminating or changing the patterns of electricity delivered to the heart. So they didn't do anything about it, by the way, until it was reported to the media. And then this past summer, this was just reported. So Medtronic, again, they make insulin pumps that are implantable. And 6 of their insulin pumps had to be recalled because they could also be hacked. Now, just so you know, both Medtronic and Boston Scientific, who are the 2 biggest makers of pacemakers and insulin pumps, are also the 2 biggest makers of implantable brain-stimulating devices. So what I am telling you is that you could kill someone and you wouldn't leave a trace. It would be the perfect crime. It's something to think about. So we're going to close this out by mentioning the final way in which we might be able to edit and hack humans. And that's through CRISPR. So there have been a few scattered talks I've seen here and there. CRISPR, for those of you who don't know what it is a form of editing the genome. You can't edit everything. You can only edit like certain kinds of misspellings that are really close together. So imagine I were typing in a Word document, and let's say I were in the United States and I typed the word color everywhere with an OR, and then I wanted to publish in a British or a Canadian journal, and I had to change all of that to OU. What I would do is a Command F, and then I would do a Command R. I would replace every misspelling with the corrected spelling. CRISPR works just like that. We hijacked the evolutionary machinery that bacteria use to kill invading viruses, and we applied it to all kinds of things. And the very first human CRISPR trials are underway right now, some of them for cancer, and in this case, for solving sickle cell disease. CRISPR is being used for some other really amazing and cool things. This is George Church. He's a very famous geneticist at Harvard, and what he's trying to do is CRISPR out or edit out viruses that little piglets grow up with, because normally we can take a valve from a pig and give it to a human who needs it, but we can't transfer entire organs because the recipient has their immune system suppressed, and this virus can kill them. So he's CRISPRing it out so you can grow up pigs that may be potential donors for humans who need organ transplants. So this kind of approach might solve our organ problem. And there's some even weirder ways to do it. So this comes from the Belmonte lab at the Salk Institute. What you see in that image is a pig embryo that can grow up into a pig. But coming in through that pipette, and this is a real picture, are human stem cells, human-induced pluripotent stem cells. And they're being injected into the pig embryo, and pig-human chimeras have started growing. In other words, you can use the pig as your artificial womb for human organs. Okay? Some other cool applications of CRISPR. We have a crisis in the world in terms of antibiotic resistance. Well, it turns out these little rocket-shaped viruses called phage like to infect bacteria. You can engineer them to more specifically kill the bacteria you want to target. And there are now companies coming up around this. But as with everything I have told you about in augmentation and editing, this is dual-use technology. And the thing everyone has been the most afraid of is what happens when people start to design babies, right? To basically choose the traits they want, height, eye color, intelligence, strength, and design the baby they want. And by the way, that will stay in the germline, so they'll pass this on to their children. And all these scientists had agreed, okay, we're not going to do this. This was a global agreement. And then suddenly at the end of 2018, a Chinese scientist by the name of He Jiankui decided he would do it anyway. And he did it to 2 embryos that were formed by IVF, in vitro fertilization, in a dish. Now, he said he did it to alter the immune cells so they would be less sensitive to getting the HIV virus. What he may have done instead is actually shorten their immune lifespan, but augmented their brains. So we may have now the first genetically super intelligent children, and we won't know really until they have grown up. So that's the kind of off-target effect that you need to be worried about. So as we close, I want you to hold a couple of thoughts in mind, because this is an open discussion. One, where does the organic human end and the digital one begin? And secondly, if we keep on digitizing humans, will it make it more possible to hack them? And I would argue that we need a heck of a lot more privacy and security than we have right now. I mean, what is our digital ethics around humanhood, right? Because if we are digitizing the neural code and we are digitizing the genetic code, we open ourselves up to reading humans without their permission, writing to humans without their permission, and manipulating them. And so as we are augmenting them, as we are treating their diseases, we are forcing humans to evolve beyond Homo sapiens and potentially making them a target for hacking. Thank you.